let's move on, try to wrap up this chapter. So we are talking about moment distributions. All right, so we are talking about moment distributions, and we said that we can try to understand the approach using several processes. All right, so we break down into the first step is trying to convert loading into the joint. So that can be accomplished by using a claim assumptions, so that you can generate the end moments, the joint moments. So that's the first step. And the second step is called balance and distribute. So you just need to balance those moments which is not supposed to be there in the first place. And then you follow by the distributions into the components. And the follow-up step would be you need to check to see whether you need to carry some moments to the far end, depending on the far end conditions. So that pretty much summarizes the moment distribution methods. So the rest is just illustrating how I can implement such a concept into problem solving. So this is a problem of continuous span, and the degrees of indeterminacy, obviously 1, 2, 3, 4, 5 is a 5-degree indeterminate structure, depending on whether you take an actual load consideration. Load not your considerations, then this become a 4 degrees indeterminate structure. Okay, so we need to solve this structure. So the first thing you need to do for moment distribution is to find distribution factor, and there are 2 places that you need to set up distribution factor. So at joint B and joint C, there are 2 components connecting, so you need to calculate the distribution factor for these 2 joints. So first is at a joint B. Joint B is distribution factor BA is KBA plus KBC. So K, depending on the far end conditions, if the far end is claimed, then it's 4EI over L. If the far end is free, then it's 3EI over L. So obviously, this is BA, far end is claimed, 4EI over L. So this is 4EI over L. So both of them are 4EI over L. So BC is a concern. So BC is looking at this component. So this is not free, and this is not claimed either. It's not free, not claimed. But it's a continuous span. But we only know 2 values. One is 4EI, one is 3EI. So which one will you choose? Should I choose 4EI or should I choose 3EI? 4 or 3? 4. The reason for that is because if I choose 4EI, I'm assuming that this side is claimed. So I can distribute based on that assumptions, but I can always relax that claim assumptions, followed by balance and distribute. So I can always take care of that if I assume this is a climb. But if I use 3EI, that means that I am assuming this side is moment-free. If that is the case, then you have no ways to correct that. You cannot, you cannot carry or transmit any moment to this side, and you cannot compensate that. So there's no way you can compensate if you do a 3EI over L. All right, so with that, then the distribution factors can be calculated. So this should be 0.5. And we know that at the joint, the summations of distribution factors should add up to be equal to 1. So you don't need to even calculate. You know that the other distribution factors will be 0.5. So that goes to joint B. Now go to joint C. Distribution factors for CB and distribution factors for CD. So follow the same logic. For CB, it's going to be KCB over KCB plus KCD. Now, so it's the same thing here. It's all 4EI, 4EI, 4EI. But notice that the length of the span or length of the components are different. So you have to reflect that. So I'm assuming that you know what I'm saying. So same formula, but the length of the components are different. So sum up to be equal to 1. All right, so here are the distribution factors. So with that, I'm ready to set up my moment distribution table. So this is corresponding to joint A, B, C, and D. So on top of the row, I put down distribution factors. So here is 0.5, 0.5, and 429, 571. So they are distribution factors. All right. So the first row is called fixed end moments, where you convert your loadings to the joint. So you need to convert this loading to the joint and convert this loading to the joint. Assume first, this is clamp. So you have a UDL apply on this clamp beam. So the corresponding moment will be WL squared over 12. So it's 1.5 times 20 squared divided by 12. Calculate that, equal to 50. And the other side, you also have another 50. So this is counterclockwise, this is clockwise. So I start out the process, put down 50 and minus 50. That to take care of this UDL loading, assuming that they are clamped at both sides. And my practice is I underline those which is coming in because I assume that it's clamped, but it's not. So this is assumed clamp, but it's actually not. So I underline this, means that I need to balance that moment. All right, that takes care of this UDL. Now let's go to this concentrate loads. So concentrate loads, again, you need to convert to the joint. So you assume that the joints are clamps. All right, so you convert that concentrate load to both sides. So you're going to develop end moments here and here. And the value of that is PL over 8. So 30 times 20 divided by 8. So that gives you 75. So you will see 75 here and another 75 here. They are applying on this component. And this is counterclockwise, so it should be positive. And this is clockwise, should be negative. So I need to double check to see whether this is coming from the climb assumptions. So yeah, they did come from the climb assumptions. So I underline those, indicating that I need to balance this. So immediately followed by this action now, I need to balance those imaginary or assumed moments. And then I can follow that directly by distributing into the components. So this is 75 minus 50, so it's positive 25. So I need to balance this by minus 25. So balance minus 25, 50-50%. So you don't have to write it out, otherwise you got confused. I'm just reminding myself. And here is 75 minus. You need to balance that with 75 positive, and then distribute according to the distribution factors into the component. All right, so that's balance and distribute. Next step is carry over. So look at the far side to see whether you need to carry over. So far side is climb. Yes, you carry over 1/2. So here, far side is not claimed. It's not free. So you let it carry over 1/2. But you put an underline there, reminding yourself that why it's carry over is because you have a claim assumption. So same thing here, 32.2. You carry over by 1/2. And the reason why you can carry over by 1/2 is because of the climb assumption. And from here to here is obviously carry over. And you don't need to underline because it's climb. OK, so now you have underline means that you need to balance. So you follow by balance and distribute again. So you balance this by negative 16.1, distribute. And this one, 6.25, distribute. Right? You see that this operations is the same as this operations. So this balance distribute, they are starting to repeat the patterns. So the next one is going to be carry over. It's going to be very similar to this carry over. So you carry over 1/2. You carry over. All right, underlying why you carry over is because you assume that it's claim, and you carry over 1/2 and try to work it out. So you see that it's starting to repeat, so you can repeat. So people ask, when do I stop? You can see the numbers decrease quite quickly. So maybe let's try one more run. 1.34. 4.02. And then carry over. All right, so it's getting into less than 1 now. So this side is a little bit higher. So you decided then we can check one more calculations. So we can do one more calculations to make sure that we have a small number. This one. All right. It's getting into below 1 for O. And then you carry over, getting smaller and smaller. All right. If you like, you can do one more step, if you like. Did I do all right? Yeah. You can do one more step if you like. So you come to natural stop, and then you need to do a summation at the end. All right, so that's the results that I obtained. So this apparently is not going to end until you call it stop. So when do you stop? You see the numbers start to get small, and you can make a decision when to stop. If you stop too early, of course, there's errors. Okay, any questions about this? All right. So let's look at this one. What happens if there's a settlement in part of your structure as well as a loading? So analyze this using moment distribution. There's only one joint, which is joint B. So you need to work out distribution factors at joint B. Obviously, K is going to be 3EI over L, 3EI over L. So if the EIs are constant, the L is constant, then obviously it's going to be split in half. All right, so we need to start. We know this now. We know the distribution factors. So we need to start from converting the loading into the joints. So we call this step like fixed moments. Now, but we need to obtain the fixed end moments for this loading, which is easy, as well as due to the settlements. So how do we obtain the settlements induced moment? So let's see. Okay, so I know that this point will be settled by 40 millimeter. So this point is going to move down 40 millimeter. Now, I know how to take care of this loading. Very simple. I just assume this is claim, this is claim, find out the moment, right? Now, can I also assume that it's claim and let it drop to these positions and see how it goes? So what I'm saying is I assume that this whole place is claim. And I assume this is claim. This is claim. So the structure deformation is going to look something like this. So I assume that they are all claim and let the deformation or settlements occur, and then calculate the induced moments and then start from there, using that as a fixed end moment. Because we can always relax this claim assumptions. All right, so previously it works pretty well if we have loading. Now I'm going to show you that it works also pretty well if this involves settlements. I can actually obtain the end moments due to these settlements. The equation I can use is slope deflection equations. So this is a slope deflection equation. So I'm saying that I want to find out if I have a loading here, and if I have a some conditions, and I let this joint drop down by a certain amount, I can come out with the end moments through these equations. Now, this is very obvious that you can do it, and you can do it very, very easily, because this is claim. So there's no rotation angle, And this is the rigid body rotation. So whatever you dropped, you say delta divided by the length. That gives you this rigid body rotations. And this is clockwise, so it should be negative. So you see, this equation, or this part, is actually can take into considerations when the structure has some sort of settlement or differential settlement. You see that directly related to the end moments. So we do have ways to find out the end moments due to the settlements. And this part, final part, is basically just to reflect the contributions of the loading. So if this is a concentrate load, then the fixed end moment, concentrate load at the midplane, then fixed end moment there is just PL over 8. So we do have ways to figure it out. So now the only thing we need to figure out is what is the rigid body rotation angle So this is 40 millimeter divided by the length of 8 meter. So rigid body rotation angle for AB is going to be clockwise, 40 millimeter divided by 8 meter. So it's minus 0.005. So this is coming from 40 millimeter divided by 8. And it's negative because it's clockwise. And this part also has a rigid body rotation. So this is phi BC is going to be 40 millimeter divided by 8, but it's counterclockwise, so become positive value, rigid body. All right, so with that, then we can utilize these equations to give us the fixed end moment. So under claim assumptions, then I can calculate MAB. So it's going to be 2EI over L. L is 8. And this is negative, negative, so it becomes 3 times fixed end moment is PL over 8. P is 100. L is 8. So this can be calculated if you substitute EI values. So this is 475. So I just give you one more calculations. MBA under settlements and loading condition is 2EI over 8. 3 times this minus so 1 plus 1 minus is because the end moments due to this concentrate load is this side and this side. So this is negative, so that's why I have a negative sign there. So this turns out to be 275. So similarly, I can calculate the end moments here, end moments there. So let me just put it down here. MBC is MCB all right. So that will be the starting point for the calculations. So we can form the moment distribution table. Oh, very loud. Let me put it down first and then see whether you have any questions. Okay, table. So start with fixed end moments, assuming that everything's are claimed, assuming everything's are claimed. So you have the induced moments. So we just calculated the induced moment is this at this side and this at the other side. So let's work in kilonewtons domain. So here the first one is 475 and 275. And then this component is minus 375. Minus 375. I put all of them underlined because they are all coming from claim assumptions. They are not supposed to be claimed, but you claim them because you need to convert the loading or the settlements to the joints. Cool? All right, so followed by balance distribute. This, nowhere to distribute, just directly balance that. Add this two up. So minus 100, you need to balance by 100, and then divide it by two components. This, very simple. Just directly balance that. Carry over. Need to carry over? Yes? No? My voice is too sexy, huh? So many of you got fallen asleep. So do you need to do any carryover? Yes? Which, from where to where? From A to B or B to A? A to B, A to B. Let's see, A to B. But this is not free, not claim, so we have to assume it's claim. Assume that to be claim. Do I need to do 50 to the other side? No, because this is moment free. No. So this side to this side. Carry over 1/2 on the line. Balance distribute. So sum up, balanced. Distribute. Any further action? Yes? No? Yes? No? Do I need to do any further action? Yeah, further action is to sum up. No need to do any distribution, carryover, but just to sum up. Because look at the far side, it's moment free. Far side, no moment free. You don't need to do anything further to carry over or to distribute. So sum up. All right, so perfect. 0, 0 on both ends, perfect. Because supposed to be 0, because they are moment free. So supposed to be 0. All right, let me stop for 2 minutes. If you have any questions, let's stop for 2 minutes. If you have questions, just raise your hand. 你呢度傳咗過嚟咧，你一定要傳啲嘢過去噶嘛，因為呢度唔係 moment free 噶嘛，你一定要傳咗過去嘅。但係咧，你只係可以傳0.5或者係唔傳嘅啫。
哦，所以我拎走咗之後，再放翻一個係唔係傳嘅？
係啦。For sure, you will see this kind of problems in the final exam. For sure, it's going to appear. For sure, you will see a slope deflection equations. And for sure, you will see a calculation of deflections, shear force bending moment diagrams. What else? Yeah, everything that I taught. Okay, any other questions about this example? No. The key here is not to memorize. The key here is to understand, because there will be so many possibilities. So you cannot just memorize. So it should not be a routine. It should be based on your understanding. And when not to carry over, when to assume is when to assume is clamp, when to assume is 4EI, when to do is 3EI. So you have to understand. Otherwise, you won't be able to solve this problem. All right, so if not, let's look at the two-dimensional problems. All right, let's look at this two-dimensional frame. Under one concentrate load and one distribute loads. I should give you the dimensions. All right, so that's the dimensions. So the first thing you need to work out is distribution factor. So you need to work out a distribution factor here and here. So there are two joints that require you to calculate distribution factors. So this is the very first step. If you see this in the final exam, make sure that you have the distribution factor correctly calculated. Otherwise, all the answer will be wrong, and then you'll go home and then see you next year. So, all right. So let me just verbally describe how you obtain these values. So look at these joints. They will be distributed between this component and that component. So you need to look at the far side. So if the far side is claimed, then the K value associated with that here is 4EI over L. So that is 4EI over L, no problems. Here, the far side, look at that, is not claimed, it's not free. So very similar to the previous example that we have. So if you assume it's claimed, you can come back and compensate that. But if you assume this is free, then there's no way you can compensate, you can calculate. So as a result, here you should use 4EI over L. So it's 4EI over L, 4EI over L, and then you can use that to calculate the distribution factors for BA and BC. Cool? So that's for joint B. And for joint C, same thing. CB, there are 3 components. There are 3 components, CB, all right. So again, based on the stiffness K, so here, look at the far side. It's going to be 4EI over L. For this component, look at the far side. Moment free is going to be 3EI over L. This, look at the far side. Moment free, 3EI over L. So it's going to be 3EI over L, 3EI over L, and then 4EI over L. So then you work out the ratio and substitute the I values carefully. So you should be able to obtain these 3 values. So use this as an opportunity to practice. Make sure that you can get those. OK? Then first step to start the process is to convert the loading to the joint. So I need to convert this loading to this joint and that joint. So this is concentrated loads at midspan. So it's PL over 8. So this is 18. For UDL converting to joint, assuming they are claimed. So it's going to be WL squared over 12. As I say that, I will not give you this 2 formula. You have to memorize. So the first one is the concentrate load at the midspan. It's PL over 8. The second one is UDL. And the moment will be WL squared over 12. Got it? So WL squared over 12. So that gives you 54. All right, so with that, we are ready to set up the moment distribution table. So this is joint A, B, C, and E. We have a D somewhere. So C actually have 3 components. C is connecting to B. C is connecting to E. Also, C should be connecting to D. So this is what I do. It's connecting to D. Connecting to D. But it's at the C. It's right here. C connecting to D is right there. And there's a possibility of carrying over to D, right? So there's a possibility to carry over to D. So I put down a D here. So this is possibility of carrying over to D. All right. Cool? So this represents AB components. This represents BC components. This represents CE component. And this represents CD component. So put down the distribution factors. Distribution factors. So it's going to be here and here. CB, CD, CE. All right, so 2 joints that have distribution factor. All right. Start the process. Fix and moments. Assuming that everything's clamped. So you have the 18 here. Applying on BC component at BN. So BC component at BN is 18. Positive because it's counterclockwise. And then this 18 is applied at C of the BC components. It's clockwise. C at the BC components, so it's minus 18 between BC components. And UDO is CE component occurring at C and occurring at E. So 54, CE component 54, and minus 54. And all of them are appearing because you have a clamp assumptions, all of them. All right, so far so good, or so far no good? Where is your no good from? from which distribution factor? Okay. Slow down. Okay. Slow down. Balance and distribute. Huh? Speed up now. Speed up. All right, balance and distribute. So balance this 18 by minus 18 and distribute into the components. Okay. Balance this and that, but they all appearing at the joint C. So you need to balance by 18 positive, negative 54. Sum up, start to distribute according to the distribution factor. balance and distribute. E, balance, no distribute. So follow that is the carryover. So here, from B to A, yeah, A is a climb, so carryover. From B to C. B to C, yeah, you have to assume climb, otherwise you don't carry over anything there. Underline. From C to B, yes, pass on 1/2. Underline. From C to E, from C to D, D is a moment free, no need to do anything. From C to E is moment free, no need to do anything. From E to C, yes, you let it carry over 1/2, and that is under the assumptions of climb conditions. So you have underlines, so that means that you need to do balance and distribute. All right, so hang in there. How many of you have problems understanding this or following this so far? How many of you can follow this and understand this? I'm talking to somebody. Yes? So far, so good? Can you pinpoint where you don't understand? Huh? Okay, yeah. Are you sure? Okay. Now we'll do that. I will do that in the final exam. It's too late. Yeah, you still have the 4th year to complete. I feel myself repeating processes. You always start from distribution factor, fixed moment, balance, distribution. The process is kind of repeating. Yeah. All right, people at the back. Hello? You guys are okay? All right, let's finish this up. I think it's repeating. Oh, it's not quite repeating. Let's say, now we need to distribute this. One more step, maybe we can start to repeat. So you need to balance that, distribute. This is called balance and distribute. And this too, balance and distribute. All right. Balance and distribute, followed by carryover. Yes. Carryover. No carryover and no carryover. Okay, so underlying. So one more time, balance and distribute, carryover. You know that it's going to be looping in the middle part, if you have time, we still have time. Let's finish this. Balance and distribute. All right, followed by carryover. Right. Yep, we start to see the repeating pattern. So you compare these two. They are repeating. So they are repeating. So you can anticipate that you're going to repeat these two process until the number gets small. And again, the number gets small, you know when to stop. You know, if you only keep 2 significant digits, so you know when to stop. So the final step for calculation is to okay. D is also 0. That's an obvious checking point for you. Point D and point E, they are moment-free. So no matter how you calculate, they should always end up 0. If not, that means that you are wrong. There's only one answer. So that's a good checking point for you. And also, at the joint, they should achieve joint equilibrium. So this is clockwise. This is counterclockwise. So they achieve joint equilibrium. So same as here. You should achieve joint equilibrium at the end of your calculations. Okay, so any questions about this? Okay, time to go into another example. On Friday, it's final lecture time for us. So I'm intended to first finish the chapter and give you a very quick overview and review of the whole class. All right, so that's it today. So see you on Friday.